So, if we move a bar magnet towards a stationary charge, the charge experiences a force due to the varying magnetic field. This is the fundamental significance of Faraday's discovery. Consider a rectangular conducting loop PQRS placed in a uniform magnetic field of strength B. The arm PQ of the loop can be slit over its arms PS and QR. Arms PS and QR of the loop are part of the rails SM and RN connected to SR. The length of SR is L. The length of the arm PS at an instant is X. Let the electrical resistance of PQ be R. Let us assume that the resistances of the rails SM, Rn and the link SR is negligible compared to the resistance of arm PQ. Hence, the overall resistance of the rectangular loop is R. The flux through the loop at any instant, phi B, is equal to the product of the strength of the magnetic field B and the area enclosed A. Here, area of the loop A is equal to the product of the breadth and length of the loop L and X. In this case, the instantaneous flux phi B is equal to BLX. Let this be equation 1. From Faraday's law, we get induced EMF E is equal to minus d phi B by dt. The negative symbol is in accordance with Lenz's law. On substituting phi B from equation 1 and simplifying, we arrive at the equation E is equal to minus dBLX by dt. The strength of the magnetic field B and the length of the arm SR of the loop L are constant. Hence, the equation transforms to E is equal to minus BLdX by dt. But dx by dt is the instantaneous velocity v of the arm PQ of the loop, which is directed towards the SR part of the loop as shown. Hence, E is equal to minus BLV. Let this be equation 2. This EMF is the motional EMF as discussed earlier. As the resistance of the rectangular loop is R, the magnitude of the induced current I is equal to the magnitude of E by R. The current is directed from P to Q in the arm. Substituting the value of E from equation 2, we arrive at the equation I is equal to BLV by R. Let this be equation 3. As the current carrying arm PQ is in the magnetic field, there exists a force on the arm. The direction of this force acting on the arm PQ is given by Fleming's left-hand rule. According to the rule, the thumb, the forefinger, and the middle finger of the left hand are stretched such that they are mutually perpendicular. If the forefinger and the middle finger indicate the directions of the magnetic field and direction of the current respectively, the thumb indicates the direction of the force. Thus, as per the rule, the direction of the force on PQ is opposite to the direction of the motion of the arm PQ. Vectorially, the force on the arm PQ is given by F is equal to I L cross B, and this force arises due to the drift velocity of charges, responsible for the current along the arm and the consequent Lorenz's force acting on them. Hence, the magnitude of the force F is equal to ILB sine theta, where theta is the angle between the directions of the current and the magnetic field. Here, the angle between the arm PQ and the magnetic field is 90 degrees. Hence, the equation for the magnitude of the force transforms to F is equal to ILB sine 90. As sine 90 is equal to 1, this can be rewritten as F is equal to ILB. Let this be equation 4. On substituting equation 3 in equation 4 and simplifying, we get F is equal to B square L square V by R. Let this be equation 5. This force arises due to the drift velocity of the charges through the arm PQ that are responsible for the current and the Lorenz's force on them. If we need to maintain uniform velocity for the arm PQ, we need to apply a constant force F in the direction of the velocity. The applied force must be equal in magnitude and opposite in direction to the magnetic force. Thus, the power required to push the arm PQ along the rails is given by the equation P is equal to FV. On substituting the value of F from equation 5 and simplifying, we get the equation P is equal to B square L square V square by R. Let this be equation 6. Notice that the work done in moving the arm PQ is mechanical in nature. This mechanical energy is converted into heat energy when the work is done. This energy, referred to as joule heat, is given by Pj is equal to I square R. On substituting the value of I from equation 3 and simplifying, we get Pj is equal to B square L square V square by R. Let this be equation 7. Notice that the right-hand sides of the equations 6 and 7 are equal, thereby confirming the law of conservation of energy. Thus, mechanical energy which was needed to move the arm PQ is converted into the induced EMF and then to thermal energy. Thus, we conclude that the induced EMF in a conductor when moved in a magnetic field is in accordance with law of conservation of energy. Let us now study the relationship between the flow of charge through the arm PQ and the flux. From Faraday's law, we have learned that the magnitude of the induced EMF modulus E is equal to change in magnetic flux delta phi B by delta T. Let this be equation 8. However, the EMF induced in the circuit is equal to IR. But rate of charge flow is current. Hence, current can be replaced by delta Q by delta T. Let this be equation 9. The left-hand sides of equations 8 and 9 are equal. Equate the right-hand sides to arrive at the equation delta Q is equal to delta phi B by R. We use an apparatus that allows a copper plate to swing back and forth through a magnetic field like a pendulum. The plane in which the copper plate swings is parallel to the plane of the plate and normal to the direction of the magnetic field. As the copper plate enters the field, the changing magnetic flux induces an EMF in the plate, which in turn causes the free electrons in the plate to move, producing circulating eddy currents. Note that the magnetic field is directed from the north pole to the south pole of the magnet that provides the field. When viewed from the north pole side of the magnet, the induced eddy current is counterclockwise as the plate enters the field. As the plate enters the magnetic field, the external magnetic flux through the plate increases. Hence, by Lenz's law, the induced current must provide effective magnetic poles on the plate that are repelled by the poles of the magnet. Thus, here a north pole is induced over the surface of the plate facing the north pole of the magnet. As the plate leaves the magnetic field, the external magnetic flux through the plate decreases. Hence, again as per Lenz's law, the induced current must provide a magnetic south pole on the surface of the plate facing the north pole of the magnet. This is quite opposite to the case when the plate enters the magnetic field. The induced eddy current always produces a retarding force FB when the plate enters or leaves the field. This retarding force slows down the swinging of the plate and eventually brings it to rest. Thus, the oscillations of the plate are damped. When rectangular slots are cut in the plate, eddy currents and the corresponding retarding force are greatly reduced. This reduction in the retarding force is because the rectangular cuts in the plate prevent the formation of large current loops. Hence, the pendulum plate with holes or slots reduces electromagnetic damping and the plate swings more freely. Let us now explore the uses of eddy currents. Eddy currents are produced when a metal plate is subjected to a changing magnetic field, heats it. Hence, these currents are unwanted in certain situations. Reduction in the surface area of the plate helps in reducing eddy currents in the metallic cores of transformers, electric motors, and other such devices, in which a coil is wound over a metallic core. Eddy currents are minimized by using laminations of metal to make a metal core instead of using a single metal piece. The laminations are separated by an insulating material like lacquer. The plane of the laminations is arranged parallel to the magnetic field, such that it cuts across the eddy current paths. This arrangement reduces the strength of the eddy currents. Since the dissipation of electric energy into heat depends on the square of the strength of the electric current, heat loss is substantially reduced. Let us now study the applications of eddy currents. Strong electromagnets are situated above the rails in some electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rails oppose the motion of the train. As there are no mechanical linkages, the braking effect of the train is smooth. Certain galvanometers have a fixed core made of a non-magnetic metallic material. When the coil oscillates, the eddy currents generated in the core oppose the motion and bring the coil to rest quickly. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. A high-frequency alternating current is passed through a coil which surrounds the metals to be melted. The eddy currents generated in the metals produce high temperatures sufficient to melt it. The shiny metal disc in the analog type electric power meter rotates due to eddy currents. Electric currents are induced in the disc by magnetic fields produced by the sinusoidal varying currents in the coil. Consider a circuit consisting of a coil having n number of turns connected to a source of EMF in which current can be varied with time. When the source current is in the direction shown, a magnetic field directed as shown is set up inside the coil. When the source current changes with time, the magnetic flux through the coil also changes and induces an EMF in the coil. This phenomenon is called self-induction. The flux linkage through a coil of n turns is proportional to the current through the coil and is expressed as n phi b is directly proportional to I. Replacing the proportionality symbol with a constant, we get n phi b is equal to L times the current I, where the proportionality constant L is called the self-inductance of the coil. Let this be equation 1. L is also called the coefficient of self-induction of the coil. When the current in the circuit is varied, the flux linked with the coil changes and an EMF is induced in the coil. This means d by dt of N phi b equals to L di by dt. Let this be equation 2. From Faraday's law, for a coil of N turns, the self-induced EMF E is equal to minus d by dt of N phi b. Let this be equation 3. Comparing equations 2 and 3, we get the equation E is equal to minus L di by dt. Let this be equation 4. It is important to know that from Lenz's law, the polarity of this induced EMF is such that it opposes the change in the magnetic field from the source current. Even Faraday's equation confirms that the self-induced EMF opposes any change of current in the coil. Thus, this self-induced EMF is also called back EMF. The self-induced EMF plays the role of inertia. It is the electromagnetic analog to mass in mechanics. Hence, work needs to be performed to establish a current in a circuit, and it is stored as magnetic potential energy. For a current I, at an instant in a circuit, the rate of work done is dW by dt is equal to modulus of E times I. Let this be equation 5. On substituting the magnitude of E from equation 4 in equation 5 and simplifying, we get dW by dt is equal to Li di by dt. Let this be equation 6. The total amount of work done can be established by integrating equation 6 on both sides. Thus, we get integral dW is equal to integral over 0 to I, Li di. Thus, the work done or energy consumed in establishing a current in the circuit is W is equal to half Li square. This expression is similar to the expression for kinetic energy of a particle of mass m moving with velocity v, which is given by E is equal to half mv square. This clearly shows that self-inductance L in electromagnetic induction is analogous to mass m in mechanics. Thus, self-inductance is the measure of electrical inertia. It opposes the growth and decay of the current in a circuit.